Welcome. As a continuation to the previous discussion, we will explore few more examples. Here, for m equals 1, 2, 3, etc., we are gonna define f m of x, which is limit n approaches infinity cosine m factorial pi x to the power 2n. Okay, so we have one such situation here. Okay, here if you notice, whenever this m pi x is an integer, that is, let us say m pi x is some p which belong to z, and we know cos px would be plus or minus 1, right? Therefore cos px to the power 2n, this shall be written as cos px square whole power n, so that would be 1 power n, which would be 1 only. Okay, for all other values, what are we going to have? So for all other values, our m factorial pi x would be, absolute of this would be less than 1. Sorry, what I am trying to say is that for all other values, our cosine m factorial pi x, absolute of this quantity would be smaller than 1. Hence, this cos m factorial pi x to the power 2n, as value of n becomes larger and larger, this will go to 0. Okay, so thus we shall write f of x to be limit m approaches infinity fm of x, and this fm of x is defined in terms of n only. Here already n tending to infinity is there, so this value is either 0 or 1 only. Okay, suppose x is a rational value, then this x shall be written as p upon q, where p and q are integers with q non-zero. Then in this case your m factorial x would be an integer whenever if your m is bigger than or equals q. Okay, so basically what is happening? Limit m approaches infinity, limit n approaches infinity, cosine m factorial pi x to the power 2n would be 0 if x is irrational, and it would be 1 if x is rational. So for each value of q, whatever may be the x that we are choosing, we would be able to do this one, and accordingly we would be able to identify an integer m in this fashion. Okay, so this discussion is valid. Here the obtained limit, the obtained limit is an everywhere discontinuous function and is not Riemann integrable as well. Okay, let us explore some more examples. Let us have fn of x to be sin nx upon under root n, where x is any real and n is running from 1 to 3 etc. And we would be able to see that limit n approaches infinity, fn of x would be what? It would be 0, right? So this is our f of x. Okay, and we are able to see that our f prime of x is also 0, and fn prime of x would be what? It would be this 1 upon under root n cosine nx into n. So it is under root n times of cosine nx, and limit n approaches infinity, fn prime of x is tending to what? It would tend to either plus or minus infinity, right? So this is okay. In particular, this would be either infinite or minus infinite. In particular, our fn prime at 0 is simply under root n, which tends to plus infinite. Therefore, limit does not preserve under differentiation. So even though it is pointwise convergent, okay, the pointwise convergent is not preserving under differentiation in this example. Okay, something interesting is turning up. Now we will have another example. Here, let us have fn of x is n square x times of 1 minus x square to the power n, where x is in this interval and n can be any integer. Okay, here for 0, excluding 0, our limit n approaches infinity, fn of x is what? This x is somewhere between 0 and 1. 1 minus x square to the power 1. So 1 minus x square means that still remains a value which is smaller than 1, and when we raise the power to a larger extent, that will be 0. So this would be 0, and directly we would be able to see that when x is 0, the entire thing is 0. Okay, thus our f of x is 0 for all x in the interval 0 comma 1. Okay, now what we are going to do is that this limit is preserving under integration or not. That is what we are going to try and see. So let us first now try to find the integral value of this one. Okay, we can make use of the change of variable technique and see that this is what we will have as the limit integral value. Okay, therefore integral 0 to 1 fn of x would be, it is just the it is just scaled by the factor n square, right? So it would be n square upon 2n plus 2, and this tends to infinite as n approaches to infinity. But what is 0 to 1 f of x dx? It is simply 0. So pointwise convergence is not preserved under integration as well. Pointwise convergence is not preserved under integration. Okay, moreover, if we define gn of x to be n x 1 minus x square to the power n, where x is taking the value in the interval 0 comma 1 and n can be any integer. Then your g of x is 0 for all x in the interval, and integral 0 to 1 your gn of x would be n upon 2n plus 2, and this will converge to 1 upon 2 as n approaches infinity. But your integral g of x dx is 0. Okay, again here this pointwise convergence is not preserved under integration, but here we are seeing the situation where the limit function, the integral of the limit function is giving some finite value, and the integral of the actual sequence is giving some other, that is converging to some other value. Okay, even though both converges, okay, here gn is also converging and the integral is also converging, but the integral is not converging to the integral value of the limit function. That is what. Okay, so even though pointwise convergence is there for all the sequences and series that we have discussed, they fail to preserve under some operation. So is there any way under which we can preserve them? That is what we are going to discuss in the upcoming lectures. Thank you.